Okay. Okay, let me start recording. Okay, couple of things I want to talk about. Let's say today the plan is I'm going to talk about chapter 5. First, finish most of the chapter 5. Then I'll give you about half an hour for the quiz for chapter 4, just one problem quiz. So it won't take too long. Before I talk about chapter 5, a couple of things I want to say. Again, project, okay. You will have one more project to go. The content will be chapter 5 and beyond. I haven't posted yet, but you can start working on it if you have some subject to do, okay. I think I will post next week, and you still have 2 weeks to do to the end of the semester, okay. So you can pick anything during the last 3 weeks of the semester, okay. Project, I'd like to also still talk about a little bit. Now I finished grading the project 2. I still feel, a small portion of you still have some problems doing a appropriate project to verify a theory. Okay, let me share my screen. Let me write down something. Many of you did better, much better. Okay, so, but still some of you, let me still spend 5 minutes on that. Okay. Okay, do you see my screen? Where's my pen? Here it is, okay. So let me use an example. Let's say buoyancy. Okay, so many of you did the buoyancy. Buoyancy is kind of easy, in the easy end of the kind of project. Okay, so say you have an object floating on the water. Let's say, let's make it simple as possible for the explaining purpose. Okay, let's say you have an object floating in the liquid, right? So if you decide to do buoyancy, you know the equation you are gonna verify. The equation will be your weight equals the buoyancy force. Okay, be careful. So if you have a floating object like this, this is the equation. If it sink on the bottom, stand on the bottom, this is not the equation. Because when you sit on the bottom, then there is a supporting force from the bottom. So you have 3 forces: weight, buoyancy, and the supporting force. Be careful. Some of you still use this equation if your situation is actually the object is sitting on the bottom of your container. Then this is not the correct equation to verify because you miss a term. Okay, so let's say this is a simple case. Let's say it floats. Okay, so well, this is the equation you want to verify, saying you have to write down this, expand this equation right into gamma times volume. So there are 4 letters. That's what I always want you to do. Based on the equation, look at the equation to design how you're gonna measure what the experiment will be. So you have 4 letters. Okay. The fundamental of doing experiment to verify theory is to verify this equal sign in this equation. Okay, does that make sense to everybody? So equation has 2 sides, they not be equal. Some of you try to do greater or less than. This is a less restricted than equal. So equation it's better. You verify equation. It's not to verify an inequation. Okay, equation is more strict. Okay, there's more restriction. So you have to verify this equal sign. So how do you verify the equal sign? So you have 4 letters here. You need to know all 4 of them. Okay, that makes sense to everybody? Please follow me. Since you are in the class, please follow. Okay, spend your focus 100%. Okay, so these 4 letters, But none of that can be obtained by this equation because you haven't approved it yet. You can't use it. Does that make sense? So you have to use independent method to get those values, okay? You can measure all four of them if you have equipment. You can measure the mass. Hey, mass is easy to measure. Use a scale, okay? You can measure G, but you don't have to. You know what G is, okay? And the gamma is a property of the fluid, okay? Maybe you know, maybe you don't. If you don't, you can measure it. If you know, that can be the value you know in the volume. It could also be measured or determined. Okay, so here, if you measure all of them, hey, then you prove if it's equal or not. Does that make sense? You don't have to measure all of them. So I want you to measure at least one of them to make it as a experiment. Does that make sense to everybody? Okay, some of you did much better the second experiment. Some of you still score relatively low. Okay, so then you decide which to measure. You say, I don't have equipment, but hey, that's fine. Can you measure a volume without even knowing without even having any kind of equipment? Maybe you have to have a cup. You mark the water line without the object. They mark the water line with the object. Okay, so hey, the total volume of this water is the volume of this object. Bingo, you did the measurement. Okay, so with the other knowledge, see if they are equal. Mass, easy to measure, right? If you have a scale, usually household, you have a scale. Hey, you can measure the object. So you need to know everything to prove this sign is equal, okay? Then the equation stands. Does that make sense? You have to know all the information. So you have to know, you don't have to measure all these four letters. You look at the equation, start with equation. You design experiment, you start with equation. Okay, start with equation, see what you know, what you don't. If you don't, then go measure. That makes sense to everybody. Don't just think about, hey, I want to do an experiment to verify buoyancy. Okay, buoyancy is heavier than the weight or less than the weight, or it will sink or it will flow. Come on, this is high school physics. You do an experiment to prove existence of the buoyancy. So what? We know it exists. Okay. The high level here as an engineer student is to verify and actually quantitatively verify this equation. Okay, that's the goal. Some of you can say, hey, I can use this equation. It's equivalent to say, it's same way to say this. Okay, let's say I can calculate the volume based on this equation. Okay, I know everything. Okay, I calculate the volume. So what? That's not verification. Then you need to measure the volume. Okay, this equation has been used here. You see, your V is calculated based on this. Then this is the calculation use this equation. There's nothing verification here. Okay, that's not the end of story. Then you calculated use this, just equivalent to you try to prove this equation equals and stands. Same thing. Okay, you calculate this to measure it. Okay, so if you feel the easiest thing to measure is the mass, good. Okay, let's do this. Now, if you need to get everything else, mass is calculated based on this. Okay, this is the calculated mass. Then go weight the object. Okay, so in order to calculate this mass from this equation, you need to know gamma, you need to know G, which you know. You need to know volume. So you need to probably measure the volume too in order to calculate this mass. Then you need to measure the mass. Okay, some of you want to measure the property of the fluid. Sure, gamma equals to mg divided by volume. Okay, based on this equation, but this equation doesn't stand yet. You have to prove it. So you calculate from this. How do you know it's right? Okay, then you can measure you need to find a way to measure the gamma independently, not using this equation, which is pretty difficult. Okay, this equation you can calculate it, but but how do you know it's right? We haven't proved this equation yet. You're using it yet already, right? That's why you prove it to measure the gap, okay? Does that make sense to everybody? But same thing for the standard procedure. Basically, you're looking at this equation. Every term you need to determine independently, either from literature, from somewhere else, and see if the equal sign stands. Okay, that's how you design experiment. Is to looking at the equation, looking for whether the equal sign stands. Okay, so why I emphasize this? That's an important purpose in the future. In your real job, you probably need to determine some correlation. For example, pressure equals to something velocity to the order of 1/3 times a coefficient. Okay, so you need to determine those coefficients, or often like that, like a Moody diagram basically is an equation like this. Okay, it's empirically, experimentally determine the equation. So hey, you do experiment, try to prove this is equal. So you need to put different values in the measurement. You measure the velocity, you measure the pressure, they're not equal, okay? Then you have to multiply by something to make them equal, then you determine those coefficients. See, experiment really related to the equation, okay? So just, you have to think like this. I just want to try to change the way you think as an engineer, okay? So think like that. Think it's not a physical phenomenon, what happened, you think, you think about the equation related to that physical phenomenon, okay? So then you probably can design experiment better, okay? Does that make sense to everybody? Is that good? Any question? I want you to be, you graduate from my class, you should be really comfortable with equation. Use a equation to represent a physical phenomena. Okay, what happened physically, you can easily think as an equation. Okay, so that's all what we learn from engineering school. Okay, all different subjects, all equations. Okay, so that's a skill. When you see if something happens, first thing is, hey, what equation am I going to use for this observation? What happens now, right? So, okay, that's why I always like you to have some kind of equations to verify, kind of design those experiments like this, okay?
I do have a question about those.
Sure, go ahead.
Surprisingly, I found that I have a hard time not going over. Like I thought it was going to be complete opposite at the beginning of the semester. Let me ask you this: like when I'm explaining something, like in some classes that I've had, they say, you know, explain it like you're explaining it to somebody who doesn't know anything about it. I can't do that in 4 minutes. So, how in depth do you want us to go explaining things, knowing that you're the only person that's ever going to watch the video? You know.
Well, still, I think I still want to say, I want you to explain it as explained to somebody who don't know anything about it. So if you can translate, now you are doing opposite. See, you do experiment, you convert the physical reality into an equation. You solved it, you prove it. Then when you try to explain to people, you have to do the opposite, try to translate that equation into physical reality. That's also a skill. I think, you see, this is the back and forth, 2 ways. Okay, now you did the experiment, and now you're in front of a camera, now you explain. Because a lot of the time your client is not an engineer, he don't know anything about it. It's your responsibility to convince your client to pay you the money for this project. Okay, seriously. So you tell him about differential equation, whatever. Come on, who understand that? Okay, so now it's the opposite side. You have to explain it better with layman's term, with, you know, people can understand. So I guess that's the 2 sides of the story.
Okay, thank you.
Yeah. Good. I want to keep seeing improvement from all of you. Okay, that's more important than just the knowledge. Everybody improve, and at the end, you know, if you improve better, I think you will surprised to see, you know, maybe you're good with this subject, and you know, that's great. Okay, so That's one thing. The other thing is for the quiz and the exam. Again, I want to emphasize one thing. For the previous quiz is so easy, super easy. So I have to grade a little bit more strict on your writing. So, okay, please make sure everything you write on the paper is crystal clear and 100% correct, like a legal documents. Anything as an engineer, people take into make it accountable for you, right? So be sure to write everything correct. The other thing is, any problem I give, I need the process. I don't accept the final answer. I don't care the final answer. I need the steps you take. Every step you take is correct. If you just give me a final answer, if the problem is 20 points, you may get 2 out of 20 only. No matter it's correct or not. I don't care it's correct or not. I want to see how you get to this answer. Okay, what the steps you take. That's the points credit I will give. Okay, so I want everybody be clear on that. Okay, because the other thing is that in an online test like this, really we need to make sure everybody do the work, and it's not just like from different sources you get the solution, get the value. So I have to make sure that. So it has to be a fair process. So it's very more important to show the steps, the process you take to lead to the answer. Okay, so just want to make sure everybody on the same page on that. So I want to see the steps. Okay. Okay. Let's continue on chapter 5. Okay, the other thing is now I see the majority of you have the textbook 10th edition as we stated on syllabus. So I think let's keep doing the same thing. I will post the homework problem according to the 10th edition textbook. But if some of you, please come and talk to each other, maybe find out what the problem is and on the red shelf. They have the same problem, but maybe with different order numbers. If you cannot find, let me know individually. I will let you know what the other problem, same as the homework problem. But the other part is I don't test you or quiz you with exactly same homework problem, so it doesn't matter. The goal is to practice. Even similar problem, not same, as long as you practice, you should be good in the quiz. Okay, so I guess that's my point. And then let me know individually if you really need to know what really the problem is. I will get back to you. Okay, I just don't want to photocopy so often the textbook and post it in our group chat. That's copyright stuff, so I don't want to do that. Okay, so if you need to know, let me know. I'll answer to you. Okay, does that make sense to everybody? Okay, so chapter 5. Last time we talked about the flow rate. So I assume everybody is good with the flow rate calculation. Flow rate is from the velocity, right? If the velocity is uniform on the cross section. Okay, then if it's non-uniform on the cross section will be, if it's non-uniform. Okay, so you need to take an integration to get this. I will assign some homework problem after today's class. I will assign all the chapter 5 homework problem. Please start to work on it. Okay, some of them will be calculating the flow rates. Okay, some of them will be the use the conservation of mass. Okay, this is the volumetric flow rate, right? Mass flow rate basically is no matter what case, since we're dealing with incompressible fluid, the density is a constant. So mass flow rate just equals to density times volumetric flow rate. Okay, so it's simple. So conservation of mass. Now, conservation of mass is basically very easy. Okay, so it's basically d mass over dt equal to summation of the mass flow rate into the system minus summation of mass flow rate out of the system. Okay, M is the total mass. Let's say CV, how about that? Something called controlled volume. So all the conservation law we talk about in fluids class, okay? All 3 conservation laws, you have to have a control volume first. Just like we discussed before, everything fluid mechanics is to study the behavior in a volume, in a space. Okay, study something, some quantity change inside certain space. Okay, we're not studying the fluid particles. Okay, we don't care about what the fluid particle is. We care about the space that the fluid passed. Okay, so you need to define a space of interest. Okay, which area, which volume you're interested? That's the first question you ask to yourself before you apply the conservation laws. Does that make sense? We give a name called controlled volume, CV. Okay, I use that a lot, CV. That means controlled volume. That means a volume of interest. Okay, so in that sense, you have to define something, define an area, that a volume that you're interested. Okay, so let's use an example to explain this. Okay, let's say I have a tank. Okay, I think let's use that homework. Oh, no, let's use a textbook example. Okay, I have that. Let's see what. Let's say example 5.4. Okay, you have a tank, and you have an inlet, and you have an outlet to the tank. There's the water level in there. Okay, so what the problem says is this: a stream of water flows into a open tank. The speed of the incoming velocity is 7 meters per second. Okay, V in is 7 meters per second, and the cross-section area A in, let's say the inlet pipe, 0.0025 meters square. Okay, so the density of this water is just water, 1,000, right? 1,000 kilogram per cubic meter. Water also flows out of the tank at a rate of, okay, outlet is different. It said outlet flow rate is 0.003 cubic meter per second. Okay, so what is the rate at which water is being stored or removed from the tank? Okay, you want me to repeat the question again? What is the rate at which water is being stored or removed from the tank? So, well, actually, it doesn't know. It doesn't know is water is being stored or being removed in this problem. Okay, first of all, you probably need to decide, does the water storing, the water level increasing? That means the water stored in the tank, right? Or the water level dropping, so the water is removed from the tank. Okay, for this situation. So by common sense, hey, you guys, this is kind of easy problem. Not even using any conservation laws. How does this thing works, right? This tank water level. How the water level gonna rise? If the water level rise, what happens? You have one inlet and one outlet.
The inlet rate would be higher than the output.
That's right, Devin. You're absolutely right. Okay, if the rate coming in is higher than the rate going out, okay, the water level gonna rise. The tank is gonna be filled. Okay, vice versa. If the outlet flow rate is higher than the inlet flow rate, then you will have less water in the tank. Okay, the water level gonna drop. Okay, so I guess that's the question. Then if you determine that if it's accumulating or removing from the tank, then what is the rate? What means what is the rate? Rate of what? This is the rate, okay? In this equation, this term is called dm dt, dmcv dt. So total mass, the change of total mass in the control volume over time. Time rate of change of the mass in the control volume, right? So that's the rate basically. Okay, so now in the conservation of mass equation, in the left-hand side is the rate of change of the mass in a specific volume, okay, in a volume that you're interested, which in this case is obvious, it's a tank. Okay, see, in other problem could be different target, Could be different volume that you're interested, but in this problem is the tank that you're interested. Okay, so that represent dm over dt representing the time rate of change of the mass in this tank. Okay, so in other words, in this particular example problem is just ask you to calculate this dm over dt. Okay, that makes sense, everybody? Okay, so what is dm over dt for this problem? Now we apply this equation. That makes sense, that this conservation mass equation. The rate of change in this tank is dictated by the inlet flow rate and the outlet flow rate. It's total summation of mass flow rate in and minus the summation of mass flow rate out. Okay, if mass flow rate in is greater than mass flow rate out, there will be positive rate. That means the water accumulating, okay, in the tank. Positive rate means accumulating. Negative rate means decreasing the volume, right? Decreasing the mass. Means emptying, right? So can we calculate the total mass in and the total mass flow rate out? Total mass flow rate in. Anybody? So let's say you have a summation in this equation, right? Summation means what? It means if you have multiple inlets, you sum them up, right? You add them up. Okay, so how many inlets do you have in this problem? That's obviously one. Okay, how many outlets? One outlet. So you don't need a summation for this problem, right? Just one inlet and one outlet. Just compare which one is bigger. So what is mass flow rate in? Give me an expression.
It's V times A.
I'm asking mass flow rate. Look at this, m dot.
Would be rho times V times A.
Okay, now it sounds correct. Okay, so here mass flow rate is rho times Q basically. This equation is always stand no matter what. Okay, then what is Q? You said Q is V equal to A. Why is Q is V equal to A? Is not this integration of V over dA. You have two choices to make here, right? For the volumetric flow rate, see, you have two choices to make, either VA or VDA integration.
We chose VA because the flow is uniform.
Yeah, we assume it's uniform. It doesn't say, actually, the problem statement, it doesn't say. If it's not uniform, it will probably say. If it doesn't say, probably it's uniform, okay? Because in those kind of small pipe inlet, we always assume it's uniform, okay? So, but in reality, it is not, okay? Small variation for velocity on the cross section, okay? But since the problem didn't state if it's non-uniform, we assume it's uniform, okay? So that's why I'll pick this equation. So easy, we can calculate the total mass flow rate in equals to 1,000 kilogram per cubic meter times the velocity 7 meters per second. The cross-section area is also given 0.0025 meters squared. Give me a value. Let me put it into the equation. I'll return off my book. So do some calculation for me. 175, 1,000. Is that 17.5? Check with me.
Yeah, that's what I got.
Okay. What is the unit?
Kilograms per second.
That's right. Okay, that's what the inlet is. So minus the outlet. What is the outlet? What equation you use to calculate the outlet mass flow rate?
Q minus delta? Not
What
delta.
is the equation you use to calculate the outlet mass flow rate? Look at this page. Is there an equation for mass flow rate?
Multiply Q times the density of water.
Yeah, Q times density of water, right? That's the equation here. Okay, mass flow rate is just directly from the volumetric flow rate, which is given as the outlet. So it's 3, right? 0.003 times 1,000, 3 kilogram per second. So is this water accumulating or emptying in the tank?
Accumulating.
Accumulating with a rate of 14.5 kilogram per second. Okay. Okay, that makes sense. So that example, I think it's very easy, but it's actually a perfect example to explain the conservation of mass equation. Okay, very easy to explain. And it tells you the meaning of each terms. Okay, the first term dm over dt is basically the time rate of change of the mass in your control volume. Okay, the time rate of change is dictated by the right-hand side of the equation, which is the mass flow rate in and the mass flow rate out. Okay, is that good? Okay, this is a simple equation. I said that mass flow rate summation, okay, mass flow rate. But think about this, mass flow rate, the velocity could be non-uniform. Okay, if the velocity is non-uniform, then when you determine the mass flow rate, you have to go through the integration part. Okay, if I give you a comprehensive problem, I will give you non-uniform velocity. Then I can challenge you, can test you. Do you know how to do the integration? Okay, to calculate the flow rate. Okay, that's possible, right? But the fundamental conservation equation is easy, right? Mass flow rate in minus mass flow rate out. But when you calculate the mass flow rate, keep in mind, it could be very tedious. You could need an integration if the velocity is non-uniform. Okay. Is that good for everybody? Okay, that's it. The chapter 5 is simple, just that one equation. Okay, let me see if I can give you more example. I think the better example is the next one. Not next one, the one after next one. Example 5.6. Let's quickly go through it. I think probably I don't have time to finish it. But I want you to remember what the example looks like. This is a very practical application. Okay, very practical application. If we cannot finish today, let's finish next time. So here you have a circular tank with diameter 1 meter. Okay. So there's the one outflow. So basically the application is this. Hey, you have a process tank in the company you're working at. Okay, it's a big tank. Okay. So after a while, once in a while, you have to clean the tank. Okay, it's possible, it's a common practice. But if you wanna, before you call the, cleaning crew come to clean the tank, you probably need to empty the tank first. Okay, a big tank take a long time to empty. You know it, right? So your boss will ask you, hey, engineer, okay, I need to call the cleaning crew to clean it. Okay, when do they need to come? Okay, so if you start to emptying it from now, how long it take for the tank to be completely empty? Then I can schedule the cleaning. Okay, so that's exactly this problem. You have, let's say you have water in here, diameter one meter. The outlet diameter is 10 centimeter. Okay, 10 centimeter. So, okay. So the question say, hey, right now initially is 2 meter. Okay. How long will it take for it to empty? Actually, it's emptying into 0.5 meter. It's not fully empty. Okay, let's say. how long it will take? Go from 2 meter, drop to 0.5 meter. Okay, don't look at the book yet. Think about it. How do you calculate it? You're an engineer now. You have a task for you now. Okay, how do you do that? So you cannot just simply say, hey, I think from chapter 4, we know the velocity at the outlet, right? I think I mentioned it in the chapter 4. Okay, you have an outflow velocity here, square root of 2gh from the Bernoulli equation, right? Okay, so you should be able to calculate the velocity based on the height. But the problem is the height is changing. When you're emptying the tank, the height is changing. It's getting less and less height. So your outlet velocity is not constant. Okay, and not constant in time. It's actually decreasing. It's less and less. Okay, you cannot just use total volume divided by the, well, you know, if the outlet velocity is constant, then your time is the total volume divided by Q. Is that right? You know, total volume for the tank, cylinder, it's a cylindrical tank, right? Circular tank. So you should be able to calculate total volume, quarter pi d squared times 2. That's the total volume. So it's volume, right? Cubic meter. So the volume flow rate is cubic meter per second. So volume divided by volume flow rate, it will be the time. That will be the total time. If the outlet velocity is a constant, the outlet flow rate is a constant. Do you agree? So if you control the outflow, if the outflow is a constant outflow, then the problem is much easier. Basically, it's just this. Okay, but now the problem is it's not controlled outlet. Okay, the flow rate is changing. Okay, it's decreasing. The velocity is changing. So you cannot just use these equations to estimate the time. It's not correct. Okay, you don't know what flow rate to use. It's changing every second. Okay. Hey, everybody, does that make sense? Okay, I want you to fully remember this. Don't when you experience it, when you do a real job in your job don't do this. When you estimate time, don't do this. Career ending job could be yours. Okay, this is not correct. Okay, so we have to use the conservation of mass equation, which is this. Hey, look at this. We have a time derivative in the first term. The time is included here. So if you can integrate it out, so you will find a time basically. Okay, that's a process you probably need to take to solve this differential equation to find the time. Okay, let's leave it to the next class. Okay, today probably it's too complicated to finish in maybe 5 minutes. So, okay, but that's the process you want to take. List this equation and solve this differential equation. Basically, this is a conservation mass equation in differential form. Okay, you can actually solve it. Solve for either m or solve for either t. Okay, these are the unknowns, right? Variables. Okay, so that's the process we're going to take. Okay. Okay, any questions before we move on to the quiz? So I will post the chapter 5 homework problem today, so you can start to practice. Okay. So the quiz for chapter 4, of course, I'm going to test you Bernoulli, right? So Bernoulli. Okay, don't worry about it. I will go through it with you. Always in my quiz, I just don't want to just let you do a problem yourself. Okay, I want to guide you. Okay, guide you through the process. Okay, so let's look at the problem first. Okay, this is one of the homework problem in both textbook, in 10th edition and as well as in the real red shelf. They have this problem, but I changed this problem. It's not the same, okay, as the problem in the, just I use the same geometry here, okay. So what it says is this, it have a free stream velocity coming towards this manometer. This is actually a pitot tube, right? Velocity infinite going to, free stream velocity, okay? Obviously, in point A, this is the stagnation tube. Remember pitot tube? Okay, so on A, the velocity is totally stopped, so it converts the velocity into pressure, right? Remember, we talked about this, okay? But in the B, okay, near the B, the flow around the B, so in here, you still have a VB. VB equals to 1.1 of the, actually, the velocity increased a little bit. Remember the helmet example we did? When the flow go around the helmet, the speed actually increases, right? From 12 meters per second to 18 meters per second. Remember that example in chapter 4? Same thing here. The flow around this B actually causing the velocity increase a little bit. Okay, it's not the direct, totally not hit on the B, but go around the B. Okay, so that's the situation. And then you connect this two end of the pitot tube into the mercury, into a mercury manometer down here. Okay, the mercury, the specific gravity is 13.6. This is airflow. Okay, let's assume the gamma is just 9.8. You can say 10. I think that's fine. 9.8 Newton per cubic meter, because I choose 1 for the air density for the air, right? 1 kilogram per cubic meter times 9.8, so 9.8. Okay, the manometer reading here is 7 millimeter. Okay. Do you know what I'm going to ask you to calculate? What is the free stream velocity? Okay, so this is the problem. Okay, I want you to write this on your paper. Okay, let's see. You probably want to draw this on the paper. I don't think you can print it now. Okay, so draw a simple, things like this. Draw on your paper. Okay, I want you to put it into another 2 locations. Here, A and B, obviously you need to use, right? It's a starting point. Okay, in the manometer, you're gonna convert the flow domain into the manometer, which is the hydrostatic, okay, region. So I want you to put another letter on the level, another 2 letters, let's say C and D. Is that what you're supposed to do? I want you to remember this process. Okay, I draw this for you, write this for you, C and D. So you need to compare eventually from A to C and the B to D. Okay, remember we did an example like this. Okay, we look at the flow field, Bernoulli, and then we look at the hydrostatic regions inside the manometer. Okay, so you need these 2 locations, C and D's. Okay, can you draw the exactly C and D on your paper also? So everybody did it? Is there anything not clear on the problem statement here?
Can you repeat what you just said about what'd you say to draw?
Oh, draw this drawing, draw this picture on your paper.
Oh, just draw it just like it is.
Yeah, just draw like this. Okay, put on the C and D. Okay, these are the 2 locations you need to use in the calculation. Okay, A and B is already there, right? A and B. Then, remember that example we did in the class? We have the flow region, Bernoulli's. Okay, then we have a manometer region. We use hydrostatic principles. Okay, I hope you remember. Okay, if you remember, it's easy for you, this problem.
Okay, so you're saying it's airflow, but the gamma is 9.8?
Yeah, 9.8. We assume airflow, the density is 1 kilogram per cubic meter. So gamma become 1 times 9.8, 9.8 Newton per cubic meter. Okay, mercury.
Okay, I got you. I thought it was like 1.24. I guess that's crazy.
Yeah, that's fine. If you want to use 1.25, I don't mind. I want to make it a little bit easier for you. I use 1 as a density, so.
Yeah, I'm gonna go with 1.
Okay. Specific gravity for mercury is 13.6. Okay, now If you don't have any question for the problem statement, let's solve it together. Okay, listen, I want you to follow my steps. When I grade the previous test, I see some of you always don't follow my instruction. You just do whatever you want to think the problem is, it may turn out to be not good. Okay, so I want you to follow the steps I guide you through. Okay, so but do the detailed calculation and then put down the detailed equations. Okay, so the starting point, Bernoulli, right? Okay, you have to write down Bernoulli first, okay, because your velocity, your unknown, v infinite, you know, is in the flow region. So that must be a Bernoulli, okay? So let me ask you this. If you write down Bernoulli equation, first step, which 2 points you want to write the Bernoulli equation about? Come on, answer me. Which 2 points? You want to create another point or that's enough?
C and D.
Bernoulli equation. You have to pick 2 points in the flowing fluid
B.
region. That's right. Is that what everybody believe? Right? Everybody agree? Okay. So now, 2 points. Okay. Let's say 2 points here. Okay. I will give 2 points for next line here. Write down the Bernoulli equation between A and B and get rid of zeros. Okay. Start now. I want to use the subscription of A and B. Okay. Write down that equation. Easily get 2 points. And you have to also show me that 0 terms, get rid of those 0 terms. Okay. So 1 line. Okay. I don't want you to write more than 1 line right now. Write 1 line, Bernoulli equations, use subscription A and B. Okay. And find the 0 terms and get rid of. Okay. Don't worry about the V infinite yet. You see, as long as you have VB, if you calculate the VB, V infinite will be calculated, right? Do you agree? Okay. So your goal is just to calculate VB. As long as VB is in the equation, I'm fine with it. Okay. This is the first step. Okay. I will give you points. 2 points here. I marked here 2 points. Let me know you're done. Don't continue. Please don't continue. Please follow me. Okay. Don't continue. If you're done, raise your hand. I will see. Okay. Good. It's not just write down the equation, but also you have to get rid of the 0 term. Okay. Just tell me which term is 0. Okay. Okay. Now I think most of you did. Now next part is very, very critical. I give 4 points for the next part. This is the first line. Next line. I want you to apply the hydrostatic principle. Now convert 2 terms of A into C, and the 2 terms of B into D. Okay. I want you to rewrite the equation in terms of C and D for the hydrostatic parts. Of course, velocity you have to leave there, all right? You cannot convert the velocity term. But in the manometer, you basically, the hydrostatic principle, which is the piezometric pressure or piezometric head, is the same between A and C, between B and D. Okay, so you can use C and D's information to replace A and B. Okay, that part is extremely important. And the 2 point each, 2 plus 2. Both sides, if you can complete transform, you will get 4 points. Okay, go ahead. This is the the key information I want to test you, okay? If you're done, you raise your hand. Good. Raise your hand if you finish. Good. Don't continue yet. I want you to remember this process of solving manometer problems, okay? I want to, in the final exam, if there's a similar problem, everybody need to do it right, okay? One or two lines more than enough for this step, okay? Previous step, just one line. So after this step, you will see an equation including P and C and D's information plus a velocity information, okay? So that's what I want to see. And then you get 4 points if you can successfully do this conversion. And still some of you didn't turn on your camera. Please turn on your camera, okay? Let's make it fair to everybody. Okay, good. Okay, seems like most of you did. Okay, so if you're still working on it, that's fine. Let me talk about the next step I want you to do. Next step, also 2 point. Now, in that equation, you have a pressure on C and the pressure on D, right? So use the manometer information to calculate the difference between PC and the PD. Okay, go ahead. Next step is to get a value for PC minus PD or PD minus PC. Okay, use the manometer information, mercury information down here. This is the next step for 2 points. You could easily tell me what the PC minus PD equals, or you can substitute that value into the main equation from the next step, from the previous step, to replace the C and D. Not replace the C and D, to replace the PC and the PD. Okay, be careful. There's other terms there. This is 2 points. Then I think you have plenty information, enough information to calculate the velocity. Last 2 point is to calculate the velocity B and the velocity, free stream velocity. Okay, so these are the 10 points for this quiz. Okay, so 1 page more than enough. I think 5 lines more than enough. Don't write like 2 pages, everything, you know, just follow this process. Okay, and now you have 20 more minutes here. It's on you. Now let me open the summation side. This is quiz 10. Okay.